So, good morning to everyone. I'm Andrea Chiocca, a PhD student at the University of Pisa, and today I will present part of my research activity at the Department of Civil and Industrial Engineering. I'm collaborating with Professor Frendo and Professor Bertini for this research activity, and this is about the influence of residual stresses on the fatigue assessment of welded joints. So, why residual stresses are important? I want to highlight that I'm talking about the residual stresses generated by a thermal process. So a thermal gradient that is generating residual stresses, as for example, the additive manufacturing or the welding in this case. So especially tensile residual stresses are often, are important because are degrading and are reducing the fatigue resistance, static strength, or buckling resistance for our components. And especially in this presentation, I will speak, let's say, mainly in the first part about how to evaluate residual stresses for the welded joint, and the second part about the fatigue assessment that we are still working on, including residual stresses for this welded joint. The case study is a tube-to-plate welded joint. This is made by a common structural steel, an S355JR, and the welding process is a gas metal arc welding, generating this welding profile as in the picture, so a not full penetration weld bead. So this is the main weld bead we are focusing on. There is another one here, but this is only, let's say, this plate, this disc is used to create a pressure chamber that is then used in the fatigue assessment to detect the through the thickness crack and then stop the experimental test. So let's start from the residual stresses evaluation. I will talk about the numerical analysis and then let's say the validation of this numerical analysis against experimental results. So, okay, from a numerical point of view, the model, as already also briefly described from Mattia, I also use a thermostructural simulation, in this case an uncoupled thermostructural simulation, where so you can say the first two images describe the entire analysis. So we have a thermal part and we have a structural part. The thermal part is describing only the thermal history in the components given by the welding process. So temperature is the result of this analysis, and we are using temperature for evaluating stress strain history in the mechanical analysis. The third analysis is always a mechanical analysis, but is used to validate this numerical model against the results. So we are calculating strains that I will explain later better, but we are calculating strains both numerically and experimentally and then comparing them. So let's start from the thermal analysis. In the thermal analysis, who is working on this knows that for this kind of analysis are usually use, for example, Goldach thermal source or Gaussian thermal sources that needs, a lot of parameters to be set. In this case, I employed a really easy thermal source. So let's say that the thermal profile was created by subsequently activating some sets of elements belonging to the weld seam at the initial temperature, that is a constant temperature. So this Ti, that is in this case is 8,500 Kelvin, is the only parameter to be set in this case for this model. And yeah, let's say that this is a really simplified thermal model, but comparing to how to evaluate this Ti, we compared temperature result during a real welding process, so through an experimental test, We performed the welding process, and through thermocouples, we evaluated the temperature in different points of the. And through this result, we set this this parameter that I want to specify. This is a fictitious parameter, so this is not physical-based parameter, but it is embedding inside all the hypotheses of this. So I used ANSYS for this simulation, and through the bird and depth method, as I said, I subsequently activated a set of elements along the weld bit to describe, let's say, the temperature field, the temperature history during the welding process. From the structural point of view, so we obtained the temperature results, and now we are applying the temperature as a nodal load for the structural analysis. I wanted only to report the important part of the, say, the model, the code behind the model, how to simulate the weld bead deposition process. So here we are selecting the nodes belonging to the weld bead that have temperature higher than the melting point. In this case, so we are also selecting the elements that, say, are attached to these nodes, and then we are deactivating these elements, so we are killing these elements. And we are doing this with an iteration, so solving the model, and we are also obtaining a result like this. So in the picture, I reported some, say, slices of the weld bead for different times during the simulation. Let's say that on the left you can see the one segment of the weld bead, and the elements here we have a really coarse mesh. I decided to use this because it's easier to, let's say, to put this in the presentation. Of course, to obtain this result, the mesh, especially close and in the weld seam, is finer. So we are, let's say, describing the solidification of the molten material in this case. And so after the simulation, we decided to, of course, validate the result. Not residual stresses result, but strains result. In this case, are relaxed strains. So how we calculated these strains? We placed different strain gauges around the weld seam, so close to the weld seam, because this is, let's say, the most interesting area. So it's the area where we can obtain the highest gradient in strains. And we placed strain gauges at different radial and angular coordinates. And of course, we placed the strain gauges after the welding process. So we needed to relieve stresses, and we did this through incrementally drilling the back of the plate. So say we can say that this is a process similar to the hole drilling, but we are speaking about a macro hole. So we cannot directly applying the formula applied for hole drilling for calculating stresses. So we directly used strains in this case. So we drilled two holes. During the first hole, it's a 42 millimeters hole. We really didn't detect anything because the strains are still in the background noise of the strain gauges. So all the results I'm reporting are referring to this, the second hole, that is 100 millimeters hole diameter. Of course, all the strains that we evaluated are functions mainly of the coordinates of the strain gauges, so radial and angular coordinate, and of the hole parameters, so diameter and hole depth. In this case, you can see all the experimental results. So I wanted to show two different hole depths. So the yellow, say, line and points are referring to a hole depth of 10 millimeters, and the blue line and blue points are referring to a hole depth of 15 millimeters. These are relaxed radial strain along the hoop coordinate. So the 0 degrees point and the 360-degree point are the same point in this case. And it's clearly visible how, let's say, away from this run-in, run-out point, that is the point which we are starting the welding process and then finishing the welding process, the relaxed strains are, say, high compared to the other angular range. For this reason, we divided, say, the results in two groups, and we separately compared them with numerical results. Moreover, we evaluated the overall experimental measurement standard deviation, only considering the group B in this case, because it's quite say difficult to understand what is the real standard deviation in really close to the run-in run-out point. So the comparison for validating the numerical model. Here it is shown the always relaxed radial strains, but as a function of the radial coordinate. This radial coordinate is the distance between the weld toe, so 0 is precisely the weld toe, from the strain gauges. So numerical results, this RVP is the representative welding process, so the numerical analysis. These numerical results are shown as a convex hull of all the results along the hoop coordinate, while the experimental results are shown for 3 different radial coordinates through mean value and standard deviation. So only to be clearer, I say we took all the strain gauges at the same radial coordinate, and we used all the, say, the strain gauges in between 0 and 360 degrees to evaluate this mean value and the standard deviation. This case for 2 different hole depths, always 10 and 15 millimeters. So we can see how, let's say, qualitatively, we have a good agreement between numerical and experimental results. In this case, yeah, I forgot, this is group B. So this is the, say, the central part. This is the part where we have this more or less constant behavior of strains. And you can see that later I will show also the group A. Here the variation in results, both numerical and experimental, is say lower. This group A, in this case, you can see that variation is higher. I reported, say, this experimental data with an X because for these 2 radial coordinates, we only had a measurement point. For this reason, we were not really able to calculate standard deviation, and we use this value as a mean value. So let's say that this part is still not, we still have not so many measurements to compare experimental results with numerical results, but we can see that even in this part, let's say the variation is increasing both for numerical and experimentally, and we have even here good agreement with numerical results. So after validating the numerical model, we use residual stresses. So here I'm reporting the residual stresses on the plate surface of the specimen. So you have to imagine that this is the plate surface, and these are the residual stresses starting from the weld toe here and here, and say going out from the weld bit. These are radial residual stresses, and these are hoop residual stresses. And let's say radial residual stresses are always positive, and they're always positive. Yeah, always positive, while hoop residual stresses are, say, mainly negative with a really high gradient close to the weld toe. In both cases, is clearly visible that this area, that is the region close to this 0 degrees, that is referring to the run-in, run-out point, there is a really high variation in results, both for radial and hoop stresses, while, say, in the quite far, we can say between 60 degrees and 300 degrees, we have almost constant, so almost axis-symmetric behavior of residual stresses. So, say, take care about this point, this region, because so the material here is affected by a double thermal process. So the, say, material is changing, and also we can see from here the residual stresses are changing. Now I will say speak about the second part, the fatigue analysis. This is still ongoing work, so I will provide some results, but I will not provide a discussion about them because we are still doing some experimental results to understand if what we are seeing is, say, is true or is depending from other sources of error. So from experimental point of view, we use the homemade test bench. This test bench is made by two actuators, independently actuated, so we are able to perform pure bending, pure torsion, or multi-axial loading. At the moment, we only perform on this specimen pure bending and pure torsion loading. The specimen we use stress relieved and as well as specimens, and as I said at the beginning, the stop of the test, of the fatigue test, is done by, let's say, through a pressure transducer, by, say, understanding when the crack is passing through the weld seam in this case. So there will be a pressure drop in the chamber and the test will be stopped. From a numerical point of view, so the numerical approach for, say, calculating some fatigue damage factors is starting in both as well in a stress relieved condition from a linear elastic analysis of the whole component. We are applying bending or pure torsion loading, depending on the case. For the as welded condition, we are starting a sub-modeling analysis on the most stressed volume of the specimen. In the as welded condition, we are initializing the sub-model with the residual stresses calculated before. While for the stress relieved, we are skipping this part, and then we are, say, we are performing the sub-modeling, the real sub-modeling, applying the displacement at the boundaries, let's say. So at the moment we have, let's say, calculated. So we are calculating critical plane factors, specifically Fatemi-Sossi and Findlay critical plane factors. I want to speak too much about them. Let's say that they are depending both on, say, the stress strain inside the material, but also from material parameters. And we, of course, we didn't say run the script for evaluating the critical plane factors all over the submodel, but only in the most critical, let's say, cross section. That for torsion, we can say that every cross section is the same, more or less. But for bending, of course, we have the maximum stresses in more or less one point. So we are taking care of calculating critical plane factors in that the maximum stress cross section to decrease the computational time. Here, I'm reporting both Fatemi-Sossi and Findlay critical plane factors for pure bending and the stress ratio equal to -1 in stress relieved and as welded condition for different, say, loading of the specimen. So here I'm reporting the load at the single actuator, but here there could be also the, for example, the bending moment. Okay. So it can be seen that, especially for Fatemi-Sossi, there is not a really huge difference between the factor So both in Fatemi and Findlay, the maximum relative error is around 4-7%. Okay, while doing this for torsion, this is the result. So we are obtaining, here are the same results, but instead of pure bending, this is a pure torsion. So we can see that the maximum relative error in this case is higher. We have an, say, is increasing of an order of magnitude. So we are around 26%, where as well is always more damaging than stress relieved. So we decided to use experimental results and plot. I only plot here Fatemi Sossi at the moment to not, let's say, use too much time, but it's similar for also Findlay. So we are plotting Fatemi Sossi critical plane factor over number of cycle to fracture. And with the dashed line, so blue and yellow, we can see the pure bending for stress relieved and as welded condition, while the continuous line is referring to torsion, pure torsion in as well in a stress relieved condition. So we can see that if there is no difference in pure bending, there is a clear difference between stress relieved and as welded condition for pure torsion. So we can see this result also from a purely experimental point of view through the range. So we can see that there is still this difference also from an experimental point of view. So let's say that both numerical model and experimental results are showing that even if for the pure bending there is no clear difference in stress relieving the specimen, there is a difference for pure torsion. So as I said before, these are preliminary results. We have to understand if this problem, or if this result is related to, for example, a different batch of specimens that we used, or is given by the stress relieving process. So with this, I conclude really fast on the conclusions. I showed numerical model both for calculating residual stresses, and we validated this model against experimental result of relaxed strains. We then used these residual stresses and we implemented these stresses in a numerical model to assess fatigue of this welded joint. And we are so now working on understanding if there is a, say, a variation in results considering pure bending or pure torsion. And we are also considering doing, let's say, some multi-axial fatigue loading tests. So I thank you, everyone. Thank you for listening. And if you have questions, I think you should write an email because we are already, say, really long in time.